So, welcome everyone to the lecture number 9 on Statistical Theory for Deep Learning. We are at the end of chapter 2 about neural network approximation, and we started already with the proof of our main result, which is theorem 2.1. You see the assertion here on the slide. You have the real activation function, you have some PC smooth function where PC greater 0, you have some interval minus a up to a with exponent d, the d-dimensional on which you approximate your function, and you have some k element n, which is the parameter which controls the degrees of freedom of your so the number, basically the number of weights is linear in k. No, it's linear in k to the power d. In your set of neural networks, you have a set of deep neural networks which have a special topology. You have many constant times k to the power k plus 1 to the power d, many neural networks of some fixed with r. Well, there should be a small r in the definition of calligraphic G, and some L, which is logarithmic in K. And then the assertion is, if you have any PC smooth function G, you can find a neural network in this space calligraphic G, which approximates this function G in subnorm on the Z minus a with exponent d with an error of order constant times 1 divided by k to the power p. And we have seen already, we can define for any such g, we can define a local convex combination of Taylor polynomials, which is the formula you see here, p of x, which has constant times k plus 1 to the power d many terms. And then you just have a Taylor polynomial, so 1 over the square root of the factorials, the partial derivative at the proper point times monomials, times some head function, which is a second product. And then this p of x approximates g of x up to the error of constants times 1 divided by k to the power p. So it suffices to show that you can find a neural network of a special topology which approximates this p by an error of constant times 1 divided by k with exponent p. And that's what we are doing next. But before I will do this, I want quickly to show because today the slides are working, to show the list of exam questions. I think it's here. I just uploaded them also on the Moodle page, and it's from the version from May 13, and I think, where did we stop? I'm not sure whether I presented already question number 9. Question number 9 is that you can define piecewise polynomial with k with power d many free parameters such that the approximation error between this piecewise polynomial, or such that, so you can find such a piecewise polynomial for any PC smooth function f, such that the approximation error between f and this piecewise polynomial on this interval is constant times 1 divided by k to the power p. So that was something easier, which I used just in the proof, where we make a modification of this one. I use the local convex combination. Then I have this Jarodsky lemma, that you can find a neural network approximation, the univariate mapping x to the power x squared, having R hidden layers, 9 neurons per layer, redo activation function, and approximates on the interval minus AA up to order a squared times 4 to the power minus R. And there's an hint which you can use, which describes the main ideas in the proof. Then question 11. From this one you construct a neural network which can multiply, which was an easy consequence. So it's this idea that x times y is 1 divided by 4 times x plus y squared minus x minus y squared. And then the last question is just the theory we are showing at the moment. So the question number 12 is prove exactly this theory, what we are doing now. Okay, so let me go back to the proof. So then I can show you again. It's here. Okay. So I just continue with this proof. The last thing which we have written on the record was it's otherwise to show, and now I go on with to show this. And what I do, I show that for each, well, this p of x is a sum, and I show a sum of constant times k to the power d many terms. And I show that for each of these terms I can find a neural network in FLR. My network space was the linear combinations of these guys with the same number of terms in the linear combination, or maybe the sum of these guys and the same number of terms in the sum, such that I can approximate each of these terms in the sum by an error of order, well, this order times 1 divided by the number of terms I need. So I replace 1 divided by k to the power p by 1 divided by k to the power p plus d. To show this, we show for any and what do we need? We need k, one of the index of the sum. We need this j1 to jk in j1 to jk. I just make them natural numbers including 0 because the upper bound comes from the sum with the sum j1 plus gd. No, it's gd. Yeah. Let's equal the q. There exists some function and this function is now from our function space in the theorem, and this function space in the theorem is the one inside the definition of calligraph G, where the FLR, and I have to write them small r instead of a capital R. Typo. FLR. And this function depends on all these parameters, of course, on the k and the j1 to gd. Satisfying well, this whole product in my term, I have to write it down again. Sorry for that. That's the first. The second is the partial derivative. It's the derivative of order J1 plus V G, where I make the derivative J1 times with respect to the first component. J2 times with respect to the second component, and so on. And I make this at this point which I use for the Taylor polynomial, Taylor expansion, which is xik. Then comes the product of the monomials. So I equal 1 to d. It's x, the i's component, minus the i's component from ik, and with exponent ji. And then comes in addition this head function, which is the product of j equal 1 to d, and that was 1 minus, and it's k divided by 2a. Times x, and I work with the j's component, and the middle point of this head function is xik. I make the positive part of this, and this whole product minus f of x should be less than, not c1 divided by k, but I make c1 divided by, maybe I make a second constant, some constant, because it won't be the same. And then we have here in the, what I want to show is that the sum of these guys approximate p by error c1 times 1 divided by k to the power p, and I achieve this by showing that the individual one has an error of 1 divided by k with exponent p plus d, and then I use the triangle inequality, look at the sum, the difference of the two test sums, then the difference of the two sums is less than the sum of the absolute values of the difference, and each time is this guy, and you have constant times k with power d many of these terms, so this gives you altogether up to a constant 1 divided by k to the power d. So that's it, yeah. For all x in minus aa. No, I think it was with capital A, yeah? Capital A. And now I told you already what the trick is last time, and I have it also here. We used our lemma from the last time. The lemma from the last time was, let me see, it should be somewhere, maybe on this slide. Hopefully. Yeah. We had some multiplication lemma. And we'll use this multiplication lemma to approximate this product here of 2D many terms, but in fact I don't use 2D many terms instead, because here I have an exponent. We forget about the exponent. I write this like xi minus xi ki times and so on ji times. So we have always the exponent 1, and then I have here J1 plus CD many products, and I can add additional 1 if I want, and then I get exactly Q products at that point. So we have Q plus a product of Q plus D many factors, which we use here. And now I represent each of these guys by a neural network with one hidden layer. Well, if you look at this one, because of, look at this head function and one component of it, x1 minus k divided by 2a up to the value of x j minus x I k j plus, and we had this trick already, this is basically, it's 0 until from minus infinity to x I k minus 2a divided by k, and then it starts like a linear function x. So it's xj minus x I k j minus 2a divided by k. If I use this guy first and make it plus, then that's the same value. So you see both terms have the same value for argument xj less than x I kj minus 2a divided by k, because then that's negative here, and this one will be greater than 1, so that's negative here, so the positive part of it will be 0 here. And then, if I arrive x I kj, then I subtract 2 times xj minus x I k j. And then if I arrive x I k j plus 2a, I add 1 times x j minus x I k j plus 2a divided by k plus. And now you make these 3 case distinctions, argument less than this value, argument between this value and this value. Now you make 4 case distinctions, then the third case is argument between this value and this value, and then argument greater than this value, and you will see each time it just gives you the right hand side. So that's basically correct. So we have this one, and now you see this is a real network with 1 hidden layer and 3 neurons. So I can compute each of these guys with a real network with 1 hidden layer, 3 neurons. So I can compute d of them in parallel using 3D neurons, yeah, in 1 hidden layer. And in addition, I compute all these guys. And here well, you have them in the input layer, but I want to make a first layer of my neural network and compute all the things which I need and multiply them in addition. So I want to transport these values in the next layer, and that you make with the FID. So we just use that the xi minus x I k that's equal to the any real number is equal to its positive part minus the positive part of the negative number. So I compute this one by xi minus x I k plus minus k I minus x I plus. You have this one. now I can use that I have colors available. And now I want to compute all we can compute all factors in this guy. Using a real network. And here you can fill in the gaps. How many hidden layers? And how many neurons per layer? What do you think? Any idea?
So we need one hidden layer?
We make it with one hidden layer. Of course, we can make it with more hidden layers too, but we make it just with one hidden layer. Correct. And now the more difficult question is, how many neurons do we need? Well, you see, how many neurons do you need to compute one of these factors? 1, 2, 3. How many do you need one of these factors? 2. Now you have to count how many do you have from the first one, how many do you have from the second one, and multiply. Okay?
So we said for the second one, the one that comes first in the product, we needed Q many.
From the second one you needed Q many. So from this one, as you go. You need Q.
Either Q or D times Q.
Hmm?
It's either Q or D times Q.
Neither. Neither Q nor D times Q. If you look at, well, how do you think, why do you mention Q here? Because I told you that instead of this J1, with exponent J1, we just make the product J1 times next to each other, yeah? And then we have D times of these products, so all together we have Q many factors, yeah? But now you have to think about how many neurons do you need for each factor. Still. And that was?
Yeah, it's 2 times Q.
It's 2 times Q. So for this guy we need 2 times Q, correct? Now maybe someone else. What is the second one?
3 times D.
3 times D, because we have D times, yeah? We have D factors and each times 3. So great. That we have done. Now we apply our lemma 2.4, but not with D, but instead with D we have Q plus 3D, because D is the number of factors. Lemma 2.4 with D replaced by Q plus 3D. To compute the whole term, well, we have to multiply with something here, yeah, but that's that's not important, yeah? That you can do in the other output layer. You can modify the weights. So next. So we compute from the output of the first layer. And then we apply, how many layers do we apply next? If you look, what is, it was 18 times D. So we make R times log 2D. We have R times log 2E. And D, we don't have D. D is Q plus 3, 2 times Q plus 3 times D. Yeah? Many layers. With 18 times D. And again, our D is Q 2 times Q plus 3D. Many neurons. The red part. This guy. And we need an obvious modification of the output layer, because the product would be just the product of these guys, but of course you can just multiply the output weights by this constant thing. See. And this results in F. So then we get our F here. Now the question is, what is the error of F? And also we have to think about what is R here. If we choose R, and I need a right bound here, sufficiently large. I meant sufficiently large because of this condition, which I don't want to write down. R greater equal than log 4 times 2 to the power 4 is exponent 2d times 8 to the power 2d. In our, we also can have to be careful what is small a in comparison with capital A, and then you need bounds on all these factors here, yeah. And but this one is bounded by 1, and these guys are bounded by 2a or something like this. So 2 capital A, because the x, I, j, k are from the interval where x lives. So you can basically get small a up to the constant equal to capital A. But I don't want to write this factor down if you choose R. Therefore I write just sufficiently large. we get. And what do I get? I want to get that the red part which I want to compute, this one, minus my f of x, and that should be less than, well, I should come up with my assertion. My assertion was something like C2 divided by k plus d. K with exponent p plus d. And another question is, what do I have to choose for r? And do I get then the right result? Because then we have some some neural network. The neural network satisfies our assertion, but the neural network should also have the proper width and the proper depth. So we have to, but the depth will depend on r. So what do we need for r? Any idea? Well, what you want to get is that the right-hand side, which you have in lemma 2.4, should be less than constant divided by k with exponent p plus d. How to choose r? Okay, is the question too easy or too difficult? One answer. Well, of course, you have to plug in d is not d, d is 2q plus 3, but basically you can ignore the whole thing in front because that's just a constant. And then what I'm asking is, how does 4 to the power minus r becomes less than constant divided by k to the power p plus d? And that should be easy, right?
Maybe the log of k to the power of p plus d.
The log to the power of k to the power p plus d, and I need the log with space void.
Yeah.
So I could make something like log to the power 4 with k to the power p plus d, and then you see it's basically a constant times the natural logarithms of k. So the depth will be something like log k. And now we have to check with our, what was our assertion? Oh no, the assertion is over. No, I have to check in the theorem again whether I get that right. Do I really get that right? Signal was here, no? Do I really get the right neural network? Well, okay, so you see what I really make is L is bigger than the maximum of p plus d times log 4k. So this is p plus d times log 4k. And then I make also the sufficiently large here. I plugged in the other one to say it was I figured out what sufficiently large means. And that's this other condition, log 4 of 2 times 8a times 2p plus 3. You can check it yourself. And then R is 36 times p plus 54 times d, and we have 36 times 2 plus 54 times d, and p is larger than q. So it's correct. And then you also see I can make it a little bit deeper, and then I will get a much better arrow bound here. Do you understand why I'm not doing this? Why don't I make it deeper and get a much better arrow bound here? Doesn't hurt me to make it deeper here, and then get a better, maybe get a better bound here, arrow bound. Will I get a better arrow bound if I make it deeper? I'm finished here. Any idea? Or, in other words, how can I modify the network such that I get a better error bound? Does it help to increase the depth with this proof? Well, if you look at the proof, we first approximate f by the local convex combination of Taylor polynomials. And then we approximate the local convex polynomial of local convex combination of Taylor polynomials by the neural network. If we increased or if we decreased the error by the approximating the local convex polynomial of polynomials by neural network. So if we increase basically this guy, it doesn't help us because the other error is still there. And we make it such that both are the same order here. So basically if you want to get a better bound, then you have to increase the Taylor polynomial. Or of course you could also make it more complicated and compute this Taylor polynomial in depth. It's more depth. But that's would be a possibility, but different kind. But basically you have to change the Taylor polynomial or the local convex combination of Taylor. What you also see, if you look at the result, this neural network, well, it's of order k to the power d, many in parallel computer networks, each have order depth of order log k and a constant width. So if you think about how many weights do you have well, the log k times the constant width gives you something weights of order log k times k to the power d, and you make an approximation 1 divided by k to the power p. So it's similar to what we had for piecewise polynomials, where we had with k to the power d, or order k to the power d many free parameters, we get an approximation of order 1 to the power k, 1 divided by k to the power p. It's actually slightly worse, but the big advantage is we have a network, so if you can approximate one function with a network, you can look at compositions of functions, and then you can approximate the composition of function by composition of networks. That we will use in chapter 4. Okay. Any questions? Then I'm done with neural network approximation. We start next with neural network generalization, but before that I will clean the backboard and make a break. It's now on my clock 10:31, so I will go on at 10:36. Thank you. Okay, so let's start with chapter 3, neural network generalization. And if some of you already thought they are in the wrong movie, because there's nothing about statistics until now, here comes the statistics. So that's the part where we deal with the kind of error which arises that the neural network is adapted to some empirical risk. Empirical risk defined by some average over observed data, but we want to bound basically the risk defined as an expectation with respect to the underlying distribution. And to do this, I will introduce results from the classical VC theory. VC stands for Wapnick-Javoneckis. And I have to confess, in the Wapnick-Javoneckis theory, there are a lot of combinatorial arguments, so where you don't need immediately statistics, but on the other hand, some of them are proven by some probabilistic arguments, so it comes back. So let me start with the motivation. And I should also tell you, we are talking about the generalization error of deep neural networks. I could do this with different techniques than Wapnick-Javoneckis theory. I could use theory of Talleyrand, from which he has developed in the last. So VC theory is basically from starting 1960s, I think 1965. So it's already old, but we will have some recent results. So our first main result will be from 94 or something like this, and the main result is a result from Peter Bartlett and co-authors, and yeah, it's the Lee Bartlett-Williamson paper, and then another result again from Peter Bartlett with 3 other co-authors from 2000, I think 17 or 18, about the VC dimension of deep neural networks. This would be 2 main results. I could also use the theory of Talleyrand about the theory about okay, I've forgotten the words. No, I really forgotten it. There's a Talleyrand theory in the empirical process, concentration of measures theory, which is much more complicated, but you don't get any better results for deep neural networks. So that's the point. But it would be more modern. Okay. So what's the motivation? I consider I degrade the variables x, y, x1, y1, and so on. And I give the motivation with regression. They are independent and identical distributed with values in RD times R. Defined on a joint probability space, so X takes values in RD. It's the description of the object, and Y is the value you are interested in. I assume that Y is real integrable. Which implies also that Y is integrable, and then you can define the conditional expectation of capital Y given capital X equal to small x, and that's the regression function. X is equal to the conditional expectation of Y given with x small x. Be the corresponding regression function. Now you consider f from Rd to R, of course measurable. You consider the problem to predict the value of y given the value of x. You want to do it such that the mean square error, you make so-called to risk the expectation of f of x minus y squared as small as possible. And then we have, because of this so-called to risk, f of x minus y squared. Well, that's equal to, you write f of x minus y as f of x minus m of x plus m of x minus y. You write absolute value squared, I just make it squared, which is the same. F of x minus m of x plus m of x minus y squared. You multiply out, you got sum of three products. First term I write is the second squared, it's expectation of m of x minus y squared. Then the second term I write is the first squared. The first squared is the expectation of f of x minus m of x squared. I write this as an integration with respect to x, which is equal to the integral of f of x minus m of x squared dx dx. And then you've got the mixed product, and the mixed product is 0. And that's the next argument where the last equalities follows from. And here I make an argument in case expectation of f of x squared infinity. And then you have the mixed product, there's a factor 2 from the binomial formula, if you forget about the factor 2. Then you have the expectation of f of x minus m of x times m of x minus y. You use that this expectation is the same as the expectation of the conditional expectation. I compute the conditional expectation with respect to, by conditioning on x. I use that the product is integrable because each of the factors is square integrable, because by assumption f is square integrable. By assumption y is square integrable, and the square integrability of y implies by Jensen's inequality for continuous expectation that also m of x is square integrable. So you have here a square integrable function, you have here a square integrable function, then the product is integrable, and then you can apply this standard trick that you can factorize out that term from the conditional expectation, which just depends on x. So we have f of x minus m of x times expectation of m of x minus y given x. And this conditional expectation of m of x minus y is the conditional expectation of m of x given x, so that's m of capital X, and minus the conditional expectation of y given capital X. But m of x, by definition, if you plug in m of small x equal to capital X, then you get the conditional expectation of y given x, so that's equal to 0. So the whole thing is 0. So you have proven this equality in case that expectation of f of x squared is less than infinity, but this equality also holds if expectation of f of x squared is infinity, because in this case you have here a square integrable random variable, here a random variable which is not square integrable, but then the difference is not square integrable, and then this one will be infinite, and also the same here. This one is not square integrable, this guy is, the total difference integral over the square will be infinity. So in this case, the assertion is true. Okay, because of, where the last thing follows in case, and I guess most of you know this already from mathematical statistics, yeah? Or from the seminar, or both. Or any questions? No? We have. Now if you look at the term here, which is the so-called L2 error, this one is an integral of a square, so it's greater equals 0. So you see that the expectation of f of x minus y squared is always greater than or equal to expectation of f of x minus y squared. And you also see if f is equal to m, then the whole thing will be equal, because this one will be 0. You also see if it's equal, then this guy must be 0, which means that the argument must be for where x almost all x equals to 0. So the unique, basically the unique solution is the so-called of the minimization of the L2 risk, is the so-called regression function. With m is the argmin from d to r expectation f of x minus y squared. And now, if you want to solve this prediction problem in practice, the optimal predictor is the regression function, but of course the optimal predictor will depend on the joint distribution of xy, which is unknown in practice, but what you can often do in applications is you can consider a sample of this distribution. So you have this IID data x1, y1 until x and yn. I let this dn. So dn is equal to x1, y1 up to x and yn, which is my data set. And I want to use my data set to construct an estimate. One possibility is to use a least square estimate. For a least square estimate, I choose a set of function fn. Polygraphic fn be a set of functions from d to r. And then I define a least square estimate. That my estimate fn. And that will be an estimate depending on my data set dn. So you have a function from r d to r, function from fn, which depends on dn, and I just, well, I cannot minimize the L2 the L2 risk over all function, but I can minimize them, just minimize them over my function set. And then I cannot minimize my L2 risk at all, but I estimate my L2 risk with an expectation by a sample average, which is the so-called empirical L2 risk. And then I minimize this guy, not over all function, because if you minimize this guy over all function, you will end up with a function which interpolates your data point x1, y1 up to x and yn, in case that the xi's are distinct, which is not a good predictor of conditional expectation, but you restrict your function space. And now maybe you see, well, that's the so-called be the regression. Let this one be the least square spirit. Estimate of m corresponding to fn. now you see, as soon as I have a function space, I have a regression estimate. And now you maybe understand why I was in the first 8 lectures so happy about defining function space. In function space using deep neural networks, we will use here deep neural networks and analyze the corresponding least squares estimate. Do you see up to that point or here what is not practical on our whole approach at the moment?
Finding the argmin.
Finding the argmin. Yeah, of course the argmin, the first point is might be not existent at all. But that's not a point, because what we are minimizing is an estimate of the risk which we really want to minimize. So you don't have to because the estimate is not accurate, so you don't have to minimize it exactly. I could also say that, the empirical true risk of my function which I choose is less than this guy plus some error of order 1 divided by n. Then it will always exist. But I have no idea how to compute it. And that's what is at the moment missing. But that we are at chapter 3. Chapter 3 is neural network generalization. We will make from chapter 2 neural network approximation, chapter 3 neural network generalization. We will make a first neural network chapter about rate of conversion of least squares neural network estimates. I can prove some nice results. And then comes the 5th chapter, hopefully I still will have time, about neural network optimization. You deal about, you have to apply here some kind of optimization procedure and get some estimate, and how does this affect the error of your estimate. Okay, the aim in the sequel will be to bound the so-called L2 error. To bound the so-called error. And that's just the integral of mn of x minus m of x squared dx dx. And similarly to my first equality, or my composition of the L2 risk of a function equal to the L2 risk of m plus the so-called L2 error, you can also this same show for some random function if you condition here on the data. And that was this what I talked about in the first lecture in this term about what you have to know about conditional expectations. So this is basically the same as expectation of mn of x minus y squared minus the expectation of m of x minus y squared of the least square estimate. And what we deal with is we want to bound this error of an estimate for an arbitrary function space and see how the choice of the function space influences this. We should have something to clean the blackboard. Questions so far? Or maybe questions to this blackboard before I clean it? Well, to bound this empirical L2 error, which is the difference between the L2 risk of the regression estimate and the L2 risk of the regression function, I consider some empirical version of it where I replace just this expectation by sample average. I call this set n. That's 1 over n, I equal 1 to n. Mn of xi minus yi squared minus n of xi plus yi squared. By definition of the least square estimate, you see that this empirical L2 risk of the least squares estimate is just the minimum of the empirical L2 risk over the whole function space. By definition of Mn, you see that Zn is equal to the infimum or minimum f and Fn over n over n xi minus yi squared. Now you look at the expectation of that, and you use that the expectation of, the expectation of the difference is the difference of the expectation. The expectation over minimum is less than the minimum of the expectations. And then you see this one just gives you the, that's equal to the, or it's less equal to the minimum over f in Fn. Then you get this first expectation, well, that's just the L2 risk of the function f, because the x1, y1 until x and yn are IID. So that is equal to f of x minus y squared, and the second expectation is equal to expectation of m of x minus y squared. Now you use our standard decomposition of the L2 risk, and you see that this difference is just the L2 error. So that's the minimum over f and Fn, integral over f of x minus m of x squared px dx. And now you might understand what I did in the last chapter. We consider here a space of deep neural networks. I have assumed here that the regression function is PC smooth. I bound this L2 error, which is an error with respect to the distribution of x, upper bounded by the subnorm error. I assume that x has bounded support. And then we can apply our results for our neural network space. So we know this guy. We know how large the expectation of Zn is. So you see what we have to bound only is the difference between the L2 error and the Zn. If I'm able to bound the difference between the L2 error and Zn, then I know what, and I want to derive, for instance, the bound for the expected L2 error. Then I write the expected L2 error is the expectation of the L2 error, which is the L2 risk of Mn minus the L2 risk of the regression function minus its empirical version, plus the expectation of its empirical version, and for the plus the expectation of the empirical version, we get some nice bound here, which we know already. So we need this equal bounds on the difference between maybe I use again my colors between this guy and say that. And basically, I don't need it between the difference of the yellow term and 1 times Zn. I could also use a multiple times Zn. Actually, we use the factor 2 here, then we get here 2 times the minimum. And some factor times. So you don't understand why I use a factor at the moment, but you will see that. And now if you look what you have a random function from some function space. You look at some expectation of it and compare with some sample average. Of course, you can easily control the difference between an expectation and some average. You use something like that. Well, you know it goes to 0 for n tending to infinity, but it's strong laws of large number. You know what the rate of conversion is. This follows from the central limit theory. You can use something like Höfting inequality to get a bound for Höfting or Bernstein inequality. You get bounds for finite sample size. But the problem at the moment is that we have a random function. And we need some trick to deal with the random function. Next. Quickly. Or any questions up to that point? And this brings me to my second section, 3.2, about uniform exponential inequalities. And for the motivation, I first forget about that I have actually here a difference. I just gone, or let me write it in section. Let me write it like in the lecture note. You need upper bounds. For terms like. In our first theory, we make it a little bit shorter. We forget about that we subtract the empirical L2 of the regression function. We just look at the empirical L2 of our estimate. Yeah, and actually don't like it. Sorry. I first write the expectation, then the simple average. That's the truth of my least squares estimate. I subtract empirical two risk. We have the problem that we consider expectation minus the sample average of over some random variable, and we don't know how to deal with this randomness in the variable, and we make a rough upper bound. We just forget about the randomness in the variable. We use that this random variable is in our function space, or this random function mn is in our function space fn. So I used look at the supremum over all f in my function space of this 2 risk minus empirical 2 risk, which we are bound by supremum over f and fn, expectation of x minus pi minus so I want to get upper bounds from term like this, and these upper bounds of course will depend on the distribution of x, y, but more importantly also on the function space. Because you know if there's just a single function in this function space, you know by strong law of large number, if the expectation of f of x minus y squared is less than infinity, that this goes to 0. You know by central limit theorem, or for us it goes to 0, and so on. But we have a function space. Due to the fact that we have a function space, and it's clear, as more complex the function space will be, as bigger this part will be here. And now you might also see that, okay, we have, for our L2 error, we have two parts, yeah? We get this approximation error, and of course the approximation error will be smaller if this function space gets larger and larger. And you get here some kind of estimation error, but this will be larger if this function space gets larger and larger. So you have to balance it somehow. And in order to describe how complex our function space is, I need the notion of covering numbers. That's definition 3.1. Okay, I have an epsilon greater 0. I have a G be a set of functions from RL to R. I have a P which describes me which norm I use, if I will use an LP norm. And I will use an LP norm where I integrate with respect to probability distribution, and this probability distribution is mu. Mu probability. And I also said for some function g from R to R, I define the LP nu norm in the usual way. So you look at g of x, take it to the power p, integrate with respect to nu, and take the whole thing to the power 1 divided by p. And then the first thing which I define is a epsilon cover of G with respect to this norm. And any finite set of functions G1 to Gn, capital N from R to R, with the property that all G in our function space are in the LP nu norm, not more than epsilon away from one of these functions. So for all G and G, there exist one index I and one to n, such that the LP nu norm of G minus Gi is less than epsilon. This is called epsilon cover of G. G with respect to my norm. First definition. Now I give you set of functions G. I give you this LP nu norm. I give you some epsilon. Then you can look at all these finite sets of functions which are an epsilon cover of G with respect to LT nu. And I ask for the minimal number of functions which you need. And this minimal number is called the LP nu epsilon covering number. Next definition. So B is the epsilon covering number of G with respect to our norm. And for this I use the notation n, then epsilon, my function space, my norm. is defined as the size of the smallest epsilon cover of G. G. And we set it infinity if no finite subcover exists. And you see that's a combinatorial term. It has nothing to do with stochastic, basically. There's no randomness in it. And now we do it in a special way. We choose mu as an empirical distribution of endpoints. So Z1n, that's Z1 to Zn. That's a vector of endpoints in RL. I define mu n of a ZA. That's just the empirical measure to the point Z1 to Zn. So it's 1 divided by n. I equal 1 to n. Indicator of the Zi of Zi. Or a subset RL. And then what I look at is any epsilon cover of G with respect to the special norm. It's called epsilon cover. Epsilon cover of G on Z1n. First point. And then I define also the corresponding covering number, where I use the notation n with index p to indicate the norm, epsilon, G, and my points. That's my covering number with respect to the LP. And it will turn out this covering number, which is the LP epsilon covering number of G on Z1n. This guy will be the right quantity to characterize or to derive our bounds on these guys here. And then we will, and I first will present two theorems where we use this covering number to describe some bounds on this difference between, or uniform difference between the expectation and the sample average over my function space. and then we will deal with how to derive upper bounds on these covering numbers. Okay, any questions? Then I'm done already. I think Monday is a holiday. Oh, yeah, Monday is a holiday. So see you next week on Wednesday. Thank you.